Welcome to this paper. We have prepared 3 video demos. There are lots of textual content in this and next section. Please pause the video to look over. In the first video, we introduce our user interface by using a synthetic data set. There are 2 parts in the interface. Left is the data exploration area that contains multiple data plots. Right is the dimension exploration area. Top right is a dimension projection plot. Each point represents a dimension. Bottom right shows the detailed information of dimensions. Each histogram shows the probability distribution of values of samples on a dimension. We can sort histograms in the list by dimension name or similarity of dimensions. Here is a data grid which shows detailed numerical values on dimensions. Users can interactively select a subset of dimensions in the dimension projection plot. The corresponding plot will be created on the data exploration area. Let's take a look at what's in each data plot. This is the data projection of a subspace. This is a navigator of the projection of all dimensions. The highlighted points in the navigator are dimensions in the subspace. The information tips are displayed on a toolbar. In the pop-up menu, we provide 4 groups of operation settings. Our interface supports multiple workspaces. Here, we create a new workspace by selecting a subset of samples in subspace 1. The dimension projection plots support a hierarchical exploration of dimension space. It can show the relationships of the dimensions of a subspace. The navigator works as global view. User can return the full dimensional space by clicking the navigator. Our interface also supports the hierarchical exploration of data space. User can create many subspaces by selecting subsets of data samples. Here, we return to workspace 1 and construct subspace 5. 4 clusters are clearly formed in the data projection of subspace 5. Users can code their interested clusters with colors and tracking the clusters in other subspaces. After tagging user-interested clusters, automatic dimension reconstruction is allowed. 2 lines regarded as reconstructed dimensions are given by LDA. The operations of rotation and translation are allowed on a line. Whether or not to create these reconstructed dimensions is determined by users. The dimension projection plot is updated. The 2 stars represent the 2 reconstructed dimensions. After tagging user-interested clusters, all dimensional histograms become stacked histograms, for showing the distributions of tagged clusters. Next, we demonstrate the coordinated works of the reconstructed dimensions and the original dimensions. We add RDA into subspace 2 as shown in data plot 6. We find that the cluster on the left of subspace 2 can be classified into 3 small clusters. Similarly, we add RDA into subspace 3. Little additional information is providing, because the 3 dimensions of subspace 3 are random noises. We double the weight of RDA in subspace 7. Then some patterns can be found in the noises. We add RDA and RDB into subspace 3. When we double weights of the 2 reconstructed dimensions, the visual clustering result of subspace 10 becomes similar with subspace 5. These experiments show that the 2 reconstructed dimensions are useful to uncover clusters masked in subspace 2 and subspace 3. This video is for the first case study in this paper. The data is a real-world data set. In this case, we will demonstrate how our approach improves the data clustering results of subspaces. We first construct 4 subspaces, and create the corresponding data plots. There are 3 groups of dimensions on the dimension project plot. These 3 dimensions in subspace 3 are closely to each other, so we construct subspace 4 contains them. In data plot 1, 3 classes of samples are linearly separable. In data plot 2, red samples are distinct. So we have a question: can we use the clustering information of subspace 2 and 3, to improve the data projections of subspace 3 and 4? We reconstruct RDA and RDB, to keep the clustering information in subspace 1 and subspace 2. These 2 stacked histograms show the distributions of samples and clusters on RDA and RDB. Next, we use RDA and RDB to update the data projections of subspaces 3 and 4. Data plot 5 shows a portion of the red samples is separated from the overlapping region. The visual clustering result of data plot 6 is pretty good. Similarly, we add RDA and RDB into subspace 4, and the visual clustering result of subspace 4 is obviously improved. Another question is proposed: if we directly add the dimensions of subspace 1 into subspace 3, would the visual clustering effect be improved? Let us demonstrate another 2 experiments. In the first experiment, we will add original dimensions of subspace 1 into subspace 3 one by one. Data plots 8 and 9 show that adding an original dimension of subspace 1 leads to a less effective result. In the second experiment, we will add all 6 dimensions in subspace 1 into subspace 3. Data plot 10 presents that simultaneously adding numerous dimensions leads to obvious changes of original cluster structure, and the result of data plot 10 is not as good as data plot 5 and 6. So, we get some conclusions. This video is for the second case in this paper. The data in this video is a real high-dimensional data set. In this video, we will demonstrate how our approach helps users construct subspaces with more meaningful cluster structures. We first construct subspace 1 with all dimensions. Subspace 1 offers little cluster information. Then, we construct 2 subspaces by selecting the 2 groups of adjacent dimensions. Data plots 2 and 3 depict that both subspaces 2 and 3 form 3 strip clusters. So, now comes the question: is there any relationship between the 2 cluster structures formed in subspaces 2 and 3? We tried to find the answer by merging subspaces 2 and 3. Unfortunately, the 2 original cluster structures are missed in data plot 4. Next, we use dimension reconstruction to find the answer. RDA is reconstructed from subspace 2. The dimension projection is updated to show RDA. RDB is reconstructed from subspace 3. The dimension projection is updated to show RDB. Here are the dimensional histograms of RDA and RDB. We directly select RDA and RDB to construct subspace 5, and data plot 5 shows that 6 clusters with clear boundaries are formed. We then use different colors to label the 6 clusters individually. Then we can track these clusters, and observe their distributions in subspaces 2 and 3. We can find the 2 cluster structures in subspace 2 and subspace 3 are totally different. To sum up, we obtain some interesting conclusions as following. This is the last video demo for our paper. Thank you for your watching.